Hello everyone and welcome to another lecture. Today we will be talking about inverse of a matrix. So let's say you have a matrix called M. It's a matrix and this is a square matrix. Let's say, alright, and we ask whether there exists some matrix called N such that if I multiply M with N, this gives me the identity matrix. Now there is a subtlety here, and the subtlety is that from our earlier discussions we saw matrix multiplication is not commutative. So in general we wouldn't be able to write Mn equals to Nm, right? So before we go on and clarify more about inverse matrices, we first have to talk about some cases that are called the left and the right inverse. So let's do that. Left inverse. So our matrix is M, and if we have some matrix N such that if it's multiplied from the left to M, this will give us the identity matrix. So this N is called the left inverse of M. Then similarly we can define the right inverse as, let's say the right inverse is now R, we denote it with R, and if you multiply R on the right side of M, you get the identity matrix. So this R is called the right inverse. Now a matrix M can have different left and right inverses, but if there exists such N equals to R such that Nm equals to Mr equals to the identity, then we can say this corresponds to some M inverse 1 such that M inverse equals to M inverse M equals to identity. This is our inverse matrix, this M inverse 1 inverse matrix, and this is the case that we will be interested in today's discussion. So how do you define an inverse matrix? Seems pretty easy that this M inverse 1 is the identity, right? This is the definition. But how do we compute it? How to compute? Well, we will talk about two approaches. Today we'll talk about one approach, and in the later lecture we'll talk about another approach. So today we want to talk about the approach where you denote the components of M inverse Ij in the following manner. Oops. And this M, let's denote it with M prime, is just the minor of the matrix M. Now in case you are confused by this formula, let's try to see an example and hopefully this will make sense. So let's erase it. So let's take a general 2 by 2 matrix first, because working with them is very easy. We want to calculate the inverse. Let's denote it with A, small a, B, C, D. You can see that the determinant of A is AD minus BC. And now we want to calculate the following. That recall that in the last lectures we have talked about cofactor and minors. So in our case we have to calculate the cofactors of both A, B, C and D. So for A, cofactor is -1, 1 plus 1, D. This is just D. And similarly for B, cofactor is -1, 1 plus 2, C minus C. For C, cofactor is equals to -1, 2 plus 1, B equals to, this is 3, right? So yeah, minus B. And for D, the cofactor is -1, 2 plus 2, A equals to just A. So we calculated all the cofactors, right? What do we do now? So what is the next step? The next step is to build a matrix out of these cofactors, where the elements, that is the I and j's, the rows and columns. For example, for A the cofactor was D. So in the new matrix you have to replace D with A. Oh, sorry. So how do we build a matrix out of these cofactors? That's the question that we were asking, right? So the idea is the following. So you have to replace each element, that is A, B, C, D, with their corresponding cofactors. This. Alright, so let's form that matrix. And that matrix is just, you put D first, you put minus C, then you put minus B, then you put A. So let's denote it with B, capital B. Now to get the inverse of A, that is for A inverse, you need to take the transpose of B, that is B transpose, and then divided by determinant of A. So the matrix that is coming from the cofactors, you have to take the transpose of it. So if you take the transpose of it, what does this become? This just becomes D minus C minus B, A. And the determinant was AD minus BC. And you can easily check that if I multiply this and this, the answer is 1, 0, 0, 1. Okay. So this is how we can determine this is how we can determine the inverse of a matrix using this method. And this will work for any square matrix, because determinant is only defined for square matrices. So that's why this inverse is also defined only for square matrices. So before we finish off, we would like to mention a few properties of these invertible matrices. The first one is that if you have A inverse 1 and then you invert it again, you just get back A. The second one is, if you have two matrices and both of them are invertible, then this following identity holds. The third one is the conjugate. If you take a matrix and you take a conjugate of it and then you invert it, it's the same as A inverse conjugate. And this will be it for today. I hope you liked it, and tomorrow we will talk about another technique that we can adopt when we are trying to calculate a inverse of a matrix. Thank you.